Okay, thanks for the introduction. So this is a work that I've done in collaboration with Gabriel Senno and Antonio Asin, that are my supervisors, and also Ali Mundimit, that is a postdoc in ICFO. So I start introducing the prepare and measure scenario, that is the simplest scenario in quantum information, and for sure all of you know. So here we consider that there is a user that, based on an input X, prepares some state rho, and this can be seen as applying some channel lambda over some input state. And then, based on another input, so they perform a measurement obtaining some outcome B. So now, if we consider that the states and the measurement applied are fully characterized, then we are in the so-called device-dependent framework. But this framework presents some problems, because imperfections can make the actual device behave differently from the theoretical model. And also, we need the assumption to perform tomography and characterize the state that we prepare. So for this, more recently has been introduced the semi-device independent framework, in which only few assumptions are made over the system. So what are the possible assumptions that we can make? So the most common are the dimension one, in which the states prepared are assumed to live in a neighbor space of fixed dimension, or the information one, in which the accessible information, that is the mean entropy of the input minus the mean entropy of the input given the output, is upper bounded. Then there is the energy constraint that says that the energy of the prepared state has to be upper bounded, so the trace of some Hamiltonian over the state is lower of a certain amount. And finally, the overlap framework that says that the states prepared admit a purification whose pairwise overlap is bounded. So if we take two purifications, two different states, and we do the scalar product, this has to be higher of a certain amount. So between these, we focus on the energy constraint, that is a framework that has been already studied in literature. And in particular, this is a very nice framework because the energy is something that experimentally is easy to compute. So let's see a bit more in detail the framework. So we already said that we are considering the energy constraint, and also we consider that the energy, the bound on the energy for each state is the same. So the value omega here doesn't depend on the input X. And also the Hamiltonian that we consider has a non-degenerate ground state and a unit gap. Okay, so we can also simplify the prepare and measure scenario. So we consider only binary input X, so we prepare only two different states, and the measurement is always fixed, so there is no input Y, and is a binary measurement. So now we introduce the correlators, E0 and E1, that are just the average outcome depending on the input, and they are made by the difference on two probability elements, and each one of these probability elements can be seen operationally as the trace of some measurement element over some prepared state. Okay, let's now start to see some result that has been already achieved in the past. So we have our prepare and measure scenario, and we consider some shared randomness between the preparation and the measurement. And initially, we assume some deterministic model. So for each input X, and fixing the input X and fixing the shared randomness parameter, we assume the outcome B has to be fixed to be always +1 or always -1. And in terms of the correlators, this translates to say that the value of E conditioned on X and lambda has to be also or +1 or -1. So if we have only this assumption, then all the correlators are achievable. So if now we consider also the energy constraint, we see that the set achievable reduces to the one in this picture. And so for now, we are considering only a scenario that is classically simulable. But if we remove now the deterministic model, then we consider generic quantum correlation, and we see that the set of correlators achievable enlarges. And so in literature, they already studied this, and they characterize exactly this set. And in particular, we can see that the dashed line here, that are the maximum of the modulus of E1 minus E0, is fixed to be 4 times square root of omega multiplied by 1 minus omega. Okay, now we can see also that this framework here is equivalent to another framework, another scenario in which, instead of having the shared randomness, we consider that in the measurement box, there is a memory that is in some state sigma m, and this state is separable with the input state of the preparation. And then at the end, the measurement is performed globally over the prepared state rho and also over the memory sigma m. Okay, so we say that this is equivalent to the previous scenario. So the set of achievable correlations is the same as before. And for this, we call this set Q omega set. That just means that is the quantum set with energy constraint omega and with separable input state. So, okay, until now, everything was already done. Now we start to see what we have done in this work. So here we consider generic input state, so they can be also entangled. And so we do the following question. So now that entanglement is allowed, is the set of correlation larger? So for sure, the set of correlation that we had before is included in the set of correlation here, given that we can take the initial state to be separable. But what we want to find is that this inclusion is strict. And so we also call this set, similarly to before, Q omega n. That just means that it's the quantum set with energy constraint omega and with the entangled input state. Okay, so we want to find this separation, and initially we consider only unitary preparations. So what we found is that we found this theorem that says that with unitary preparation and with energy constraint, then the input-output correlation that we can achieve are inside the set Q omega set. So here there are no new correlation. So we move on and we consider generic mapping lambda. And what we do is to maximize the difference between E1 and E0. And so we can write it as a combination, the probability of having some output given the input under a fixed energy bound omega. And we optimize over the Hamiltonian, over the input state, the quantum channel applied, and the measurement. And again, the goal is to find now some new correlation. So we want to violate the maximal value that was achieved in the classical correlated scenario. So this quantity here 4 times square root of omega, 1 minus omega. Okay, so formally, we can write this maximization in this form, in which we just replaced the probability to have some output given the input with the operational form. And here we optimize over these 4 different variables. So this optimization is very complicated to perform, also because we are not imposing any bound on the dimension of the Hilbert space considered. So what we do numerically is to consider that the system S and the system of the memory are a QB system. So in this way, we will find only a lower bound over this maximization, given that we are restricting the dimension. And we can also rephrase the problem. Instead of optimizing over the initial share state sigma and over the channel lambda, we can directly optimize over the state that is actually prepared raw. And so now we have this optimization over 3 different variables. The Hamiltonian can be fixed considering like the ground state to be equivalent to 1 element of the computational basis. And then so we perform the optimization, finding a lower bound through a seesaw method. So the seesaw method, we just alternatively optimize over the measurement, taking fixed state, and then over the state, taking fixed the measurement. And every step of this iteration will be an SDP. So we can perform this optimization, and we found this curve. So in orange, we see the actual value that we found with this optimization. And we see that there is a violation of the value that was achievable in the classically correlated scenario, so with only separable input state. So here the gap is not so big, but then we consider instead of qubit a Q-treat memory, and we see that the gap becomes bigger. And we also try to increase the memory system and also the system of the prepared state, but we didn't see any improvement in this maximization. Okay, all until now was only numerical, but then we found also an analytical result. So we found 2 analytical states, psi 0 omega and rho 1 omega, that are the 2 states that are prepared depending on the input x. And with this state, we can numerically achieve the maximum value of E1 minus E0 that we found in the QB scenario. So in this picture, in this plot, we can see in green the value achieved of E1 minus E0 using these 2 states. And this is the exact value that we found in the first plot, in which we were maximizing over a qubit prepared system S and also a qubit memory. And then in orange, there is the maximization that we performed with the Q-treat memory, while in blue, still the case with classically correlated, so only separable state. Okay, and similar result has been found in this paper, The Role of Entanglement in Energy-Restricted Communication and Randomness Generation by Carlos and Armin, and Carlos will give a talk about this just after this talk. Okay, so I hope you follow it until here. So we have this higher violation in this scenario, and now we want to find some application of this higher set of correlation. And we found two different consequences, one in randomness certification and one in channel discrimination. Okay, so let's start with the first one, randomness certification. So now we go back to the scenario in which we have only shared randomness between the preparation and the measurement. And we consider that there is an adversary that knows the channels that are applied, the measurement, and also has access to the shared randomness parameter. So what we do is to compute the guessing probability of the adversary, given that the input x is fixed to 0, so the adversary has to guess only when the input is 0, and given that there is the shared randomness parameter and also the energy constraint. And in this work from Van Imbeck and others, they found a way to write this guessing probability as an SDP, so we can exactly find the value of this guessing probability. And now the idea is to compute this quantity with the quantity that we can find in another scenario in which we have actually some some entanglement between the preparation and the measurement. So again, we consider an adversary that knows the channels and the measurement, and also he has a purification of the initial global state. So, okay, we again want to compute the adversary guessing probability of the output, given that the input is fixed to be 0, given that there is the energy constraint, and also we have a constraint that says that the observed correlations in 1 minus E0 have to be constrained to the maximal value without entanglement. So why we put this constraint? Because the idea is that the honest user sees some correlation that are achievable without entanglement, but actually there could be some entanglement state between the preparation and the measurement, and so maybe the adversary could use this entanglement to guess with higher probability the outcome. So let's see operationally this guessing probability how we can write. So this is a maximization over the Hamiltonian, over the measurement pi, and over some states, a set of states, sigma e, that are the state that the honest user has after applying the channel lambda, and after that the adversary has performed a measurement over the state. So these are the post-measurement state conditioned on the fact that the adversary has obtained the outcome E. And the guessing probability is just the sum over all the possible outcomes of the probability that the honest user find the outcome E, while the adversary also obtained the same outcome. And we have the constraint on the energy and over the observed correlation. Okay, so this we can perform this optimization, again fixing the Hamiltonian and using a seesaw over the measurement and over this collection of state, and find lower bound to the guessing probability. And here there is the plot. We can see that the mean entropy, that is just minus the logarithmic of the guessing probability, substantially decrease when there is entanglement. And also we can observe that for omega that goes from around 0.32, the randomness goes to 0 up to numerical precision. And so this means that the adversary can always guess the outcome in this region. So from the perspective of the adversary, the outcome is deterministic. So to give a bit of intuition why there is this phenomena, we can look at another phenomena similar that relates the deterministic correlation for a fixed input. So, okay, so we can go back to the classically correlated scenario in which we have only some shared randomness between the preparation and the measurement. And so has been found that the set of correlators when the input is fixed to be 0, which arise from convex combination of deterministic behavior with the energy constraints, is given by these two inequalities. So we are fixing for each value of lambda the E0 lambda to be +1 or -1, and this is the set of correlation that we can achieve. So now if we fix that for every lambda, these correlators have to be always +1, then we have also that E0 will be 1, and from these inequalities, we can find that if E0 is 1, then E1 has to be lower bounded by this function of the energy omega. So we want to find something similar to this in the energy, in the entanglement assistance scenario. And so we fix E0 to be always 1, and we compute the minimal value that is achievable of E1 with the energy constraint. So this quantity, this minimization can be rewritten in this form, in which we just write E1 and E0 in terms of the probability of the outcome given the input, and we put the energy constraint. This again, as before, can be, we can perform the optimization using a seesaw over the measurement and over the states, and here we found an upper bound. Before we were always found some lower bound, here is an upper bound because we are doing a minimization, and with seesaw you go through feasible point and you try to reach the minimum value in this case. And so here there is a plot of this minimization in orange, and we find that the value of E1 that we can reach is lower compared to the case in which we have only classically correlated input. And so now if we have a point that is in between these two curves, so if we assume that there is only shared randomness, so for sure E0 cannot be 1 because it's violating the minimum value reachable of E1, while in the entanglement assisted scenario could still be that E0 is 1. Okay, so this was the first consequence. Now we shift to another problem, that is channel discrimination. So in channel discrimination, the task is a bit different because now the channels that are applied are fixed, and the idea is to understand how well it's possible to distinguish between the two channels. So if we have a picture like this in which we just prepare a state and then we measure, then the distinguishability is given by a function of the induced trace norm of the difference between the two channels, while if we allow some entanglement between the preparation and the measurement, then the distinguishability is given by the diamond trace norm of the difference of the two channels. So now we introduce this quantity named entanglement advantage ratio, that is just the fraction of the guessing probability of understanding which one is the channel applied while there is entanglement, so with the diamond norm, compared to the case in which there is no entanglement. And the idea, so our goal, is to find that this quantity, when there is an energy constraint over the prepared states, is greater compared to the same quantity without the energy constraint for some channels. But so how we find the two channels that satisfy this property? We can remind that we had two analytical states that were achieving some higher correlation, some new correlation when entanglement was allowed. So maybe using these two states, we can construct two channels that apply on some input states, reconstruct the two analytical states, and these two channels will be maybe some good candidate to satisfy this property. So we can suppose that one of the two states that we have in non-analytical construction is the initial shared state, and then one of the channels will be just the identity because we want to reconstruct this channel. Then the other channel will be a channel that maps this initial state to the other channel that we had in non-analytical construction, rho 1 omega. And so in this way, we have our candidates that are the identity and this lambda omega, and we compute the entanglement advantage ratio both under energy constraint and both without energy constraint. And we found the following. So in orange, we have the entanglement advantage ratio under energy constraint, actually a lower bound to this quantity, while in blue, there is an upper bound to the same quantity that is unconstrained. And we see that for each value of omega, this quantity under energy constraints is higher, so entanglement is helping more in channel discrimination when we have the energy constraint. But we can also claim a stronger result because there is this theorem that says that given a quantum channel that has a distance from identity that is higher than 1/2, then the entanglement advantage ratio has to be lower of this constant that is around 1.2. So okay, now we can plot this constant, so it's the dashed and green line, and we see that for some value of omega, our channels can, the advantage under energy constraint with our construction can go above of this bound. And so I want to stress that this theorem holds for every channel, so it's not that has only to have this restriction over the distance, while we found a specific construction that can beat this theoretical bound while there is the energy constraint. Okay, so with this, I want just to recap. So at the beginning, we proved that entanglement assisted enlarged the set of achievable correlation in prepare and measure scenario when there is the energy constraint. Then we found the first application in random certification, and we saw that the presence of entanglement can reduce the amount of entanglement of randomness that can be certified, and in some cases also reaching zero for some value of omega. And finally, we applied it to channel discrimination, and we provided an example in which one channel is the identity, and here the entanglement advantage ratio exceed both the unconstrained case for the same pair of channel that we had, but also the maximum achievable in discriminating the identity from any arbitrary channel. So with this, I want to thank you for the attention.
Thanks for the nice talk and nice results. Questions? Hi, thanks for the talk. It maybe is a bit silly question, but when you start with this constraint on the energy, on the ensemble of Alice, when you go to the entanglement assistant, would it make any difference if you consider the energy of the system that Alice is sending to Bob, but also the couple with the system coming from the source? I mean, this joint system from Alice message and also the source. Would it make any difference?
So if you consider, I don't know if I understood well. So you have the constraint on the energy like we were putting, you're considering, but there is some correlation with
the source, with the part of the state, entangled state that is going to Bob.
Okay, but so this is the point. So you have some correlation with that.
Yes.
So there are new correlation that can achieve between input output correlation when you have this correlation with Bob.
Yeah. But my point is the energy of this joint system.
We don't care of the energy of the joint system. You care only of the energy of the system that you are preparing. But actually, this system is entangled with another system that is already in your measurement box. But so this is the point.
Okay, thank you.
So I'd like to ask if there is some intuition behind the fact that when you increase the memory, I think the Hilbert space dimension, you actually increase the set of correlations achievable. And when you increase the dimension of the prepared state, you don't. So why exactly that there is any intuition?
Yeah, it's a bit complicated to understand exactly what's going on. And yeah, I don't know exactly, because I mean, we were starting to characterize a bit for qubit, understand a bit why there is this advantage in having entanglement, but then going to higher dimension becomes very complicated, and becomes complicated to understand if there can be some higher advantage. So with higher dimension, I don't have a good intuition. So maybe with qubit still you can understand something, but higher, I don't know exactly. So yes.
That's fine.
Yes. This is...
No, it was just to add that in the classically correlated case, the dimension of the prepared state can already be assumed to be a qubit, and you get all the set of correlations.
I can ask him later too. Okay. Yeah, no, thanks for the very good talk. I think I got confused about I'm just gonna ask a clarification question, because here the presence of shared entanglement actually reduces the amount of randomness that you can certify. So then I think I didn't understand the scenario very well, because the thing we usually think is that if you have more entanglement, you're going to have more security, but this is not what you have in this scenario, right?
The point is that the adversary can be correlated to this entanglement. So it's a resource for the adversary in this case, because you are finding the worst scenario. So if you don't consider entanglement, so for sure it has to be as bad as not having entanglement, because you can have, so given that you are considering even that can be entangled, you are looking for the worst case scenario. So, okay, so it could be separable and will be the same as before. So if there is some entanglement, maybe the adversary can have some correlation with this entanglement and try to guess from that. So it's a resource for the adversary in this case.
Okay, I think I get it. So the most secure thing ever would be if there's no correlation whatsoever. You just prepare some.
Yes. At the end, like if you have a pure state, then the adversary cannot be. So more restricted scenario you have, worse is for the adversary, because he can less understand. No, there are less things that he can do.
Okay, cool.
Yeah.
Well, let's think of it again.
Thanks.